All right, let's begin. This is the beginning of chapter 8. We're going into 8.1, and this is just a review of systems of linear equations. Remember systems where you have more than one graph or more than one line or more than one equation that you're solving for. Two variables just means we are in two-dimensional space. So I think you guys know this here. This whole concept of solving a system graphically, solving a system by the substitution method. I think you've heard that one before, or the elimination method. And then we're going to look at a example or a application problem here. So let's go for it here. What does it mean to have a system of equations? It just means you have two or more equations at the same time. We're trying to solve for this and this at the same time. We're trying to solve both of them. All right. So we have x and y pairs that we want to do. We're gonna again, you can do it graphically. You can do it by the substitution method. You could do it by the elimination. We're just gonna try to do all three of them at least as a review of algebra. All right, so here it is. First, before we get to the graphing method, can you verify that certain thing is a solution? And so the question is 2, 2, is that a solution to this system? That could be a solution to one of them, and that's still not a solution to the system. It has to be a solution for both equations at the same time. So let's go for it here. For A, we're going to plug in a 2 for the x value, a 2 for the y value. And when we find out, yeah, it works for the first equation. That's cool. We're going to do the same thing for the bottom, though. So multiply or put in the 2 for the x value for the bottom equation, 2 for the y value, and that's going to be 3 times 2 is 6, 6 minus 2 is 4, and that does not work. So okay, so therefore this one is not a solution to the system. It's a no. Alright, so let's try 1 and 3. Is that a solution? Here for the top equation, 1 plus 3 is 4. That's easy enough there. We know that one. That is true. So then we go to the bottom one. 3 times 1 minus 3. Would that give us a 0 value? And checking that out, 3 times 3 is 3. 3 minus 3, hey, that works. So notice 3, 1 works for both of them. And so that's a yes on the homework as I looked it up. It seems like what you do is from the possible solutions, you're going to write down the ones that are actual real solutions. In this case, you're going to write down 1, 3 in parentheses. All right, how do we actually solve these systems? Well, 3 different ways: by graphing, by substitution, and by elimination here. So let's do the first one here just to review stuff. Do it graphically, and probably the best way to do it, you could do it by doing intercepts. Remember, intercepts works, the intercept method of drawing a line. You can also solve these for y, so that's what I'm going to do. I'm going to solve these guys for y. There's my first equation. I'm going to subtract x from both sides and get myself y is equal to negative x plus 2. So my slope is negative 1 over 1. My b value is 2. I'm ready for graphing there. This equation, second equation. Move the 4x to the other side, gives us a negative 4x minus 1. And there it is. My slope is negative 4 over 1. My b value is negative 1, or my y-intercept. Let's graph them, and the whole point here is to see where they intersect. That is what the graphing method is all about. So first one here, we're going to start off at 2 because of the b equals 2, and then we're going to go down 1, 1 to the right. So down 1, 1 to the right, down 1, 1 to the right, and we can keep on going. We can do this on forever, as long as you get a pretty good straight line, because you're trying to figure out where these guys intersect. So you want to make sure that you do hit that intersection point. And so if you want some graph paper, maybe that would be a good way to do it here. If you just want to make sure that you draw a straight line, or maybe use a straight edge. So what I did is I also went backwards. I went up 1, left 1, up 1, left 1, up, left, and I ended up at this little dot right there. Okay, so I could use a straight edge from here, making sure I line up all these lines, and then it should end right about here. So there's my straight edge arrows, because lines always keep on going. And that is a pretty good straight line there, I gotta say. I think I can probably get in cross points real good here. All right, let's start with the other one here. So B value is -1 this time. And we're going to go down 1. 1, 2, 3, 4. 1 to the right. 1, 2, 3, 4 down to the right. And then instead of going down 4, 1 to the right, we can actually go up 4, 1 to the left. So 1, 2, 3, 4. Because -4/1 isn't that the same thing as 4 over -1? Those two mean the same thing. All right, so 1, 2, 3, 4. Ooh, I think I got it. Now if I went a 1 up, 4 up, sorry, 1 to the left, I hit this little dot right here, which is also on the red line as well. After that, I really don't need to go any further because I got what I wanted. I've got the intersection point between the two. I've graphed my first line straight enough to see where that intersection point goes. And what is the intersection point? Name it and you're done. So that looks like it's -1, 3. So -1, comma, +3 is the solution set. Well, that's exactly what we're going to be doing here. All right, before we start, we're going to say sometimes the answers kind of turn out to be weird. So let's go for it here. Let's take a look at all three cases. What are the three different possible answers to these type of problems? The first case, which is what we just saw here, this is called the one solution case. The two lines intersect at a single spot, and with that we call this a consistent system, and sometimes the equations are said to be independent, and the answer is just A comma B. The other possibility is that you got lines that are parallel lines to each other. So parallel lines, the answer is no solution, and the system is called to be an inconsistent system. All right, and then the third possibility, what happens if the pink line or the red line and the blue line are on top of each other? Eventually it makes the same exact line. All right, we call this what's happening graphically. The graphically it's called lines coincide. Lines really are right on top of each other. The system is called a consistent system, and the equations are dependent. Okay, the consistent and dependent stuff, that's really for later on in mathematics, where you use systems. You take a whole semester, start looking at systems, but at least you see the vocabulary here. All right, let's go for it here. The directions say use the substitution method to solve. All right, with the substitution method, how we do that is we look at these equations here. Now this is set up for elimination, if you remember from previous semesters here, because once you create opposites here, great. But a lot of times in mathematics we do use the substitution method. And so how do we do it? Well, we take one equation that's easily or readily solved for a variable. So x minus y is equal to 5. I think I could solve this one easy for x, move the y over. Or over here, I can actually solve for y over here, moving the 2x over. It doesn't matter which one you start with. You're going to get the same thing anyways here. I just chose the top one right here. X minus y is equal to 5. And then the easy one to solve for is just the x. If I add add y to both sides, you get this one here. So students always ask, Mr. H, is it 5 plus y or y plus 5? It doesn't matter. Those mean the same thing. Once I solve for one variable, now what I'm going to do, I'm going to plug it into the other equation, equation number 2, and I'm going to substitute the x as y plus 5. So let's go for it here. All right, this one's just to show you that I could have solved for y as well. I could have went this way here, subtracted 2x from both sides. Then I would have been plugging in the y value over here. So again, I just chose not to do it that way. If you chose to do it this way, that's fine. All right, so let's go with what we did over here. We're going to rewrite this. Once we get to the x value, we're going to change it up as 5 plus y plus 7. So can you solve this one for the y value? And then we'll figure out what the x value after that is. So distribute the 2. 2 to the 5 makes 10. 2y Let's see, gather the y's together. So I have 2y plus another y makes 3y. So 3y is equal to 7. Then at this point, how about subtract 10 from both sides? If you subtract 10 from both sides, 7 minus 10 is negative 3. Therefore, y has to be a negative 1. All right, with that then, what we're going to do here is we're going to back substitute what we know here. Since y is negative 1, now I know what x would be. As I plug it into this one, knowing now a piece of the puzzle right there. So x equal to 5 plus a negative 1, or x equals 4. And I'm done. All right, well, how's it written? It's always x goes first, then the y value. So the answer to this one is 4 comma negative 1. If we were to graph it like we did for practice problem number 2, we'd find that these two lines intersect right at 4 comma negative 1. All right, let's go with this one here. Systems of equations here. Now, practice problem number 4 does tell you what kind of system you're going to have. So attempting to solve an inconsistent system of equations here. So there's inconsistent systems of equations. Let's go for it. So using the substitution method still, we're going to pick a variable to solve for. Now this one, notice this one's a negative 2x, a 6y. If I were to solve for any of these right here, in fact even this one, I'll get fractions on my hands. I don't want that. The only one that's not going to give me fractions is if I solve for this x right here. And so in this case, x minus 3y is equal to 1. I'm going to add both sides 3y, and I'm going to get myself x is equal to 1 plus 3y. All right, I'm going to start rewriting the second equation. When I get to x, I'm going to substitute 1 plus 3y into the mix right there. So how about this? Negative 2, 1 plus 3y plus 6y equals 3. All right, distributing the negative 2 over. How about negative 2 minus 6y is equal to 6y is equal to 3. And then here's our little problem. Notice when we put the y's together, they will cancel. And after that, there's no more y to solve. So if your variables go away completely, and these two are not equal to each other, if they're not equal to each other, we put a slash through the equal sign and we say no solution. So there it is. That would be the answer to this one. And that's the answer to practice problem number 4, any of the homework problem. I just want to show you, but what's happening graphically here? What's happening graphically with these guys is we really have just two lines that are parallel to each other. That's all. That's the reason why we have no solution. They're never going to cross each other. There's never going to be a coordinate that is going to be the solution to both. All right, practice problem number 5. Solving a dependent system. Again, that's going to be a little different as well. Just like the previous problem though. Notice there's a 4 here, a 2, and a 6. If I were to solve any one of these here, most likely will turn out to be fractions here. As I look at the equation, I'm thinking let's solve for y first. This is the only one that's going to allow me to not have a fraction here. So off to the side there, negative 2x plus y equals negative 3. I'm going to add 2x to both sides, and I'm going to write it as y is equal to 2x minus 3. I just like to use y equals mx plus b form, that's all. All right, so let's start rewriting the bottom equation, or equation number 2. And x is fine, but when we get to y, we substitute it with 2x minus 3. There it is equal to 6 still. And let's solve this one all the way down. So distributing the negative 2 here, let's look 4x on the outside. Negative 2 times 2 is negative 4, so negative 4x. And negative 2 times negative 3 is positive 6. All right, the x's, oh, there it is. X's went away, but this time, not like practice problem number 4, this time 6 is equal to 6. That is a true statement. So if it's a true statement, I think in previous semesters, I think you wrote, remember, infinitely many solutions, or infinite number of solutions. Okay, that is a correct answer, but we can do even better than that. We can actually give what the solutions are. That's what we want to do here. All right, so here's what we do. We say to ourselves, really, what is the relationship between um, the x and the y values? And so if we say, you know what, for every x plugged in, remember these two lines are right on top of each other. So this equation here and this equation here, they are the same exact thing, right? So notice, if I were to plug in x, the question is, what's the y value look like? Or what's the formulation for the y value? If you look back over here, here's a relationship. Y is the same thing as 2x minus 3. So here's our formula that fulfills both the top equation and the bottom equation. So instead of putting x comma y, we're going to put x comma and the formula that the y value takes in to make those. So those are actually the solutions. And we're saying there's an infinite number of these solutions, and here's the formula for it. So if x is equal to 0, well, the y value is going to be negative 3. If x is equal to 1, then it's going to be 2 minus 3, or negative 1. If x is equal to 3, then that means the y value is going to be 6 minus 3, or 3. So 3, 3. So it kind of gives you a little formula for it. All right, just to prove that these two are the same exact equation, notice I get, for the top equation, when I solved it for y, I got y is equal to 2x minus 3. Let's do this here. Let's take this bottom equation down here. Let's solve this one for y. I just want to see if it gets me the same exact equation that I had before. So what I did is I subtracted the 4x to bring it to the other side. And I'm going to divide everything through by negative 2. And notice I get the same exact equation. If solving the bottom equation, solving the top equation, so that tells me these two lines are pretty much the same exact line on the graph. All right, and just real quick here, review of the elimination method, just so you have it. Remember, for the elimination method, what you want to do is you want to have opposites. So you look at these numbers here, 3 and 9. They're not opposites. 2 and negative 4, they're opposite signs, but they actually are not exact opposite numbers. In order for get opposite numbers, I think this would have been a 4. If this was a 4, that'd be great. All right, you could have also done it right here over here. This is a positive 9. If we could only make this into a negative 9, or if you say, you know what, if we were to multiply this guy by negative 3, we would have created opposites here. If we were to multiply this guy by a 2, you would have created opposites with the numbers in front of the y value. In fact, that's what we're going to do. Let's use that one right there because that's easier. Because we're not multiplying by a negative number, we don't have to switch any signs around or anything here. So top equation, there it is. First equation, second equation. And we're going to multiply the top equation by 2. Now, some textbooks, when they do this, they leave the equation unchanged. They just leave nothing. They don't put anything right here. Some textbooks, what they put NC, and just so you know, as you go back to through your work, you can kind of see, hey, did I change anything or not? So NC just means no change. No change. So for the top equation, here it is. Multiply everything through by 2, makes a 6x, 4y, and a 6 on the other side. No change for the bottom equation, and we have exactly what we want. We have created opposites for the numbers in front of the y value, or the coefficients of y. And as you add them up, 6x plus 9x makes 15x. The y values are gone. That's exactly what we wanted to in the first place. There it is. On the other side, make a 6 plus 4 is 10. And when we divide both sides by 15, yep, we're going to get some fractions here. And that fraction is 2/3. All right, so now I have a choice. You can plug into the top original, the bottom original. You could also plug into the equivalent equation. That's 6x plus 4y equals 6. That would have been okay to plug into as well. So any one of those, whichever one you like. I'm going to plug into the original top equation. That's what I want. So as I plug in, the 3's are gone, as kind of sort of as I planned anyways here. So I got 2 plus 2y is equal to 3. I'm going to subtract 2 from both sides. It's going to give me a little 1. Divide by 2 gets me a 1/2. There it is. So the elimination method gave an answer of 2/3, comma 1/2. All right, that is part of it. All right, there's my solution using the elimination method. Again, this is just a quick sort of review of it. All right, and an application section here. This is called the equilibrium point. This has to do with supply and demand curves. In this case, it can be just straight lines to make it a little easier on us. What a supply and demand curve does is it looks at market forces. And what it does there is it says, look, if you raise the price of something, there'll be less demand for it here. And so there is an equilibrium point where pretty much if you put a certain price on something, it matches the demand that's in the market right now. But really, this is the same exact thing as systems of equations. You got one equation, you got the second equation. So if you want to match these up, you can kind of go one of two ways here. Notice both of them are solved for P, or for price. If that is the case, we can go either one of two ways. We can put this second equation, we put it into the first equation, or we can take the first equation, put it into the second equation. You sort of have choice here. I'm going to do it the second way. I'm going to put the first equation into the second equation. Since they're both solved for P, I'm going to take that value, which is 20 plus 0.002x, and set it equal to the bottom equation here. All right, so if you want to deal with negatives or decimal places, that's fine. I don't like them. So I'm going to figure out, like, I need to move 1, 2, 3. I need to move 1, 2, 3, 3 times in order to make this a integer value. I need to move it 3 times here. So technically what I'm going to do, I'm going to multiply everything by 1,000. So 20 now becomes 20,000. This becomes 2x as planned. 77 now becomes 77,000. This becomes 8x. All right, let's solve for x. We're going to add 8x to both sides. That should give me a 10x over here. Still leaves us with 77,000 on that side. Subtracting 20,000 over here leaves us with 10x is equal to 57,000. And when we divide by 7, we're just going to knock off one of those zeros on that side. And that should give us an answer of 5,700, or 5,700. Okay, so what does that mean? Well, we don't know yet. We just know that the number of units that we're going to sell is 5,700. But let's now plug it back in. Again, either the top or the bottom equation, doesn't matter. So let me rewrite this here. I got an answer of 57,000 from the previous one. I'm going to put it into the top equation. All right, if you want to use a little calculator, that's fine too. 57,000 times 0.002. That gets me an 11.4. Adding that up gets me a 31.4. Okay, so the answer to this, the x value, since that was inside the equation, the p value, since this was what the equations were equal to, but this does not make sense in a sense. So what does that mean? The normal way you do it is x is the number of units that you want to sell, so it'd be 5,700 units. And then the price for it would be 31.4. Now, this could be in terms of millions, this could be in terms of thousands or billions. So we don't know because we don't have an actual sort of application problem itself that we're doing. So in that case, we are done.